Hello, my name is Fahad Al Hassoun. I am a PhD student at the MIT Human Mobility and Networks Lab advised by Professor Marta Gonzalez. I will be talking about the paper titled City Scale Next Place Prediction Through Similar Strangers. Starting with the literature of how the pattern of human mobility has been investigated, first attempts started showing that human mobility is not similar to random walks and experience high regularity. Attempting to discover and model the regularity of the behavior, researchers started identifying patterns of periodicity in human mobility. Leskovic et al. Proposed the Gaussian mixture model in which the goal was to capture the periodicity of movement. The most common example of such mobility pattern is the daily travel between home and work. Researchers also investigated the exploratory nature of human mobility. Those are the trips people make to try a new restaurant, for example, or visit a friend's house for the first time. On the other hand, Liu et al. Had an information theoretic approach to human mobility where they measured limits of predictability of how humans move based on their phone data. They show a model that can approach the limits of predictability of human movement. We use the model later in the presentation as a base case for the approach discussed in the paper. The dataset for this study consists of 1 month of call detail records from the city of Riyadh in Saudi Arabia with around 1800 towers. The data provides CDRs for the duration of the month of December 2012 from a major telecom operator in the city. Phone activity for about 300,000 users during 1 month period makes about 109 million records in the CDRs. Similar to the dataset of this case study, previous studies on similar datasets, specifically CDRs, have shown that human communication patterns are highly heterogeneous, with some users using their mobile phones much more frequently than others. Figure A on the right shows the distribution of the number of records per user, where the majority of users have a few number of location records. This elaborates on the sparsity of information about users. Intuitively, it will become harder to predict human mobility given fewer data points about their movement. The number of visited locations shown in Figure B, where the majority of users are mostly located in a few locations. This is partially due to the few number of records, in addition to the fact that users are mostly seen at home or work. In addition, on Figure D, phone calling activity along the time of day peaks during the daytime and has a minimum during the night where there is less data to model movement. Finally, Figure C shows a degree distribution of the social graph of phone calls, resulting from reciprocal phone communication, showing that the majority of users have fewer social contacts in the dataset of CDRs. A piece of information to derive certain model choices later in the presentation. The model developed by Liu et al. Shows that a Markov chain approaches the limit of predictability in human mobility using phone data. We will use the model as the baseline model in this paper. However, the approach doesn't make use of social contacts or similar strangers' mobility pattern. The Markov chain only learns from individuals' historical records and thus doesn't couple information of others. The model proposed by Liu et al. Handles human mobility as a Markovian process where people transition between locations with associated transition probabilities. The model proposed handles human mobility as a Markovian process where people transition between locations with associated probabilities called transition probabilities. Here we propose a model for human mobility as a Markov process incorporating information of movements of others. Each individual's transition between locations is intuitively related to how the rest of the population is moving in an urban setting. The model aims at utilizing such information to better predict human movement in the CDRs. The figure here shows a schematic of the proposed dynamic Bayesian network model. The nodes L1, L2, up to Ln correspond to the towers of locations visited. Each node Li depends on the last visited location a user was observed in, as well as the location of the closest sequences depending on the distance measures used. In addition to the data of an individual, the model uses the information of others to improve the accuracy of the prediction. The observed nodes or locations of others, denoted Y, correspond to the locations of others that would help improve the prediction of the model. We propose to add information of users in a similar urban settings who are not necessarily within the social circle of the user we are modeling. Our approach is to employ similarity measures, defined here, on both the temporal, spatial, and spatiotemporal dimensions of the data to find users who will potentially help in predicting the location of a given user. To that end, we couple users who have maximal temporal similarity, that is, they have data at the same times of the day, or spatial similarity, that is, they visit similar locations, or spatiotemporal similarity, that is, they visit similar locations at similar times. And we use these scores to define the most similar strangers. The plot below shows the kernel density estimation of these scores against each other. We split the data into 3 training periods, the first 1, 2, and 3 weeks of the data. Then for testing, we predict the location sequence for the remaining time, that is 3, 2, and 1 week respectively. The table shows that coupling with social contacts information, that is the method adopted by Sadilek et al., doesn't improve the accuracy and sparse data compared to other data sources. Furthermore, our method of coupling with non-social contacts that are closest spatially temporally or spatiotemporally improves the accuracy over the Markov chain baseline. The differences in the change in accuracy between the distances and the different distance measures is minimal as shown in the table. The figure on the right shows that the average accuracy of predicting the location of users varies according to the time of day. Both the Markov chain and the dynamic Bayesian network algorithms have higher accuracies where people are usually at home relative to the remaining hours of the day, where the average accuracy drops, indicating a less predictable movement during the day, potentially due to the more exploratory behavior during the day versus late at night. The coupling of mobility information of similar strangers in the DBN increases the predictability during the daytimes, while not influencing the accuracy significantly during the late time. In addition, the average accuracy of predictions fluctuates in varying degrees around the day. It is because phone calling activity is lower during the nighttime compared to the rest of the day, as shown in the descriptive data statistics. The scarcity in data during nighttime causes the average prediction to have the larger confidence intervals. Approaching the data with an information theoretic perspective and thinking about the limits of predictability of individuals, we measure the distribution of entropy and predictability of the population in the dataset. 3 entropy types were calculated in the dataset. First, random entropy, denoted S superscript rand here, incorporating the number of distinct locations visited. Then the uncorrelated entropy is superscript uncorrelated, incorporating the frequency of locations as well, or better known as Shannon entropy. The real entropy is superscript real, incorporates the sequence information in addition, in the temporally sorted locations visited. On the right hand side is the predictability limit distribution as well, of the users based on their calculated entropy. To calculate the predictability, we adopt a similar approach to Liu et al. Using Fano's inequality to calculate the predictability of each user in the dataset. Here we look at the relationship between real entropy, denoted as real in the previous slide and here as well, to the number of locations a person visited and the accuracy of the model. On the left, the entropy and the number of uniquely visited locations are shown. The entropy of a location sequence, i.e. user mobility data, increases as the user explores more location. The figure shows that the majority of the user's population visit few locations and have relatively low entropy. On the right, the figure shows the negative correlation of the prediction accuracy and the entropy of users' data is real. Taken together, these results demonstrate that reporting accuracy of a method as a single number for the entire population is not a very informative measure given the high variability within the population behavior. Thank you all for listening, and if you have any questions, I would be happy to answer them, and send them please to my email shown in the bottom of this slide. Thank you.